Hi, welcome to Lab 4 where we explore the motion of an object as it oscillates on a spring. In this lab, we use Newton's second law to predict the motion of an object as it interacts with its surroundings. Specifically, in this lab, we explore weight force, or force due to gravity, and spring force, which is motion due to a spring. Properties of a spring that can be extracted to predict motion are the period, stiffness, and stretch of the spring. The period is the time it takes for one oscillation. The spring stiffness is the measure of a spring's resistance to stretch, and stretch is the change in length of the spring. In this lab, we also use the energy principle to see how an object interacts with its surroundings at certain points in its motion. This is the video being analyzed in Tracker. We analyzed the motion of the object along its x and y axis. We also are able to extract its length at rest and the mass of the object. What is the difference between using the x and y coordinate for estimating the period of oscillation? I just told you that we examine the motion of the object along the x and y axis. We are able to extract a different period of oscillation from each of these analyses. In the x direction, we get a period of 1.582 seconds, and in the y direction, we get a period of 1.488 seconds. For this lab, we want to use the period of oscillation in the y direction because it more closely reflects the oscillation due to the spring, since the spring runs around the y-axis. Now we can extract the spring stiffness. From the textbook, we get the equation for period. We can rearrange this to solve for the spring stiffness since we know the period after our analysis. From this analysis, we get that our spring stiffness is 7.17 newtons per meter. Now we can find the relaxed length of the spring by setting the force of gravity equal to the force of the spring, giving us the following equation. This can be rearranged to solve for the relaxed length of the spring, which we found to be 0.151 meters. Here is the computer model that we generated. In this model, the red ball represents the observed position and the blue ball represents the predicted position. Here is the computer model that we created. First, we started in lines 42 through 63 by inputting the constants that we just calculated. We are then able to calculate the stretch of the string by subtracting the current position of the spring from the origin and subtracting it from the relaxed length in lines 65 through 68. We then set up a calculation loop. In this while loop, we first calculated the force of gravity, then calculated the force of the spring, added the two forces together to give F net in line 94, and then used Newton's second law in lines 98 and 100 to update the position and velocity of the object. We then updated the force of the spring, giving its new stretch, in lines 102 through 105. Here is the difference between my predicted and observed position. There are discrepancies in the computer model and the observed model because the computer model doesn't take into account things such as drag and energy loss to environment, as well as human error during the tracker analysis. Therefore, we appear to have a steeper slope in the computer model. Energy of the system. For the prediction of motion using Newton's second law, the system was chosen to be just the mass at the end of the spring. However, for the analysis of the energy of the system, we can choose the system to be the Earth, spring, and mass so that there's no outside interactions on the system, and E total is constant. For this system, we will have that the change in energy of the system is equal to 0 because there's no work, and this is equal to the kinetic energy plus the potential energy of gravity plus the potential energy of the spring. These are the necessary equations for calculating this. Here is the code that I wrote in order to address these equations. First, we started by calculating the kinetic and potential energies by translating those equations that I just listed into the ones written in lines 89 through 92. Then we set this equal to the initial energy values. Then we calculated the changes in energy by subtracting the final energies from the initial energies. This gives us the following graph. As you can see, denoted by the orange line, the total energy is always 0 because there's no outside work being done on the system. This means that our energy principle is satisfied. Since there's no work being done on the system, the change in energy is equal to zero. And we can say that the total energy, which is the kinetic energy plus the potential energy, is equal to zero. In conclusion, given only the motion of a spring, we can create a computer model that predicts the motion of the spring relatively accurately. In addition, using fundamental principles such as Newton's second law and the energy principle, we can extract properties of the spring and the energy of the spring throughout its motion. Thank you for watching.